no. You should stay.
I see. Oh, okay. Yeah, sounds good. Are you? Good. Oh, yeah, great. It's good. Your first one. I see. I see. Yes.
I also don't know.
I can help. You think I can help? Depends on which one. It's true for most problems.
But is it a standard manual?
There's sort of a system to install, but it's not get all the things that get uploaded to our server.
Oh, I think we have IDC
All right, let's get started. So we have 3 talks this afternoon, a longer day. The first 2 are back-to-back, no breaks. Both are on non-interactive proof systems from lattices, the latest and greatest. And Hoeteck will get us started by talking about SNARG for P or poly from SIS.
All right. Great to see everyone again. So I'll be talking about SNARGs for P/poly, not P, from SIS. This is work that will be appearing in crypto this year. So in this talk, I'll be talking about SNARGs for deterministic computation. So not MP like most of the workshops so far. And in particular, think deterministic computation like a function f that's computed by, say, a Turing machine, which corresponds to P, or by a circuit, which corresponds to P/poly. So here we have a prover who wants to convince a verifier that f of x is equal to y. Right? So we have the standard requirements that the proof should be very small, and we want verification to be very fast. So it should be much faster than the verifier computing f of x by itself and checking to see whether it's equal to y. In this talk, we're going to be mostly focusing on circuits. In the setting of circuits, this fast verification requirement is inherently impossible, because just to read the circuit is going to take time that's linear the size of the circuit f. Right? Instead, we're going to focus on a preprocessing model where the verifier is allowed to do some preprocessing on the circuit f that could potentially take a very long time. And after that, given the information that it gets from this preprocessing phase, it should be able to run verification very quickly when it gets the input x on the same computation f, on the same circuit f. So this is SNARGs for deterministic computation. And the main result of this new work is all right, then when fast verification, we mean that the online verification time is fast. So the main result of this new work is basically the title of the talk. We get SNARGs for circuits from the SIS assumption. Note that it's a non-interactive argument system and no random oracles, so this is a standard model. In particular, we get a scheme with a constant sign CRS. So here, throughout, the big O notation hides factors that are polynomial and security parameter. So constant sign CRS, the proof size is linear in the depth of the circuit, and the verification time, the online verification time of the preprocessing is essentially optimal, so linear in the length of the input. Moreover, we get a transparent setup, by which I mean the CRS is uniformly random, and we get unambiguous proofs. This means that you cannot even, that the proofs for true statements are computationally unique. So you cannot produce 2 different proofs of the same statement, even for accepting instances. And I think what's really exciting, at least for me, is that this work presents a new approach for constructing SNARGs that's simple, direct, elementary. So by simple, direct, elementary, I mean roughly at the same level as some of the existing parent-based schemes in the work of, that's listed over there. And in particular, there's no Fiat-Shamir, no CI hashing, no PCPs, no bugs. So if you don't know what any of these acronyms mean, it's fine, because the operative word here is no. And more importantly, there are no prerequisites. In particular, you don't need to remember anything from the previous talk. Right, so nonetheless, let me compare with the prior construction of SNARGs. So we have SNARGs for P, from the LW assumption and from sub-exponential DDH. So compared to this works, compared to LW-based schemes, our assumption is better. SIS is weaker than the LW assumption. And compared to sub-exponential DDH, we get post-quantum security. Okay. Okay. However, our work is does fall short of what's achieved in prior works. In particular, we get a relatively large proof size that grows with circuit depth, whereas prior works achieve constant size proofs. And moreover, our results only work for circuits and not for P. So P is sometimes harder than circuits. And a minor minus, depending on who you ask, is that even though we're able to avoid a lot of the heavy machinery, there's going to be a lot of algebra in this talk. I'm sorry?
Yeah, P/poly is larger than P, but he has a long CRS. And, if you talk about P, you can hope to get like a constant size CRS.
If the CRS is constant
Not
size,
CRS.
because the CRS is small.
Oh, sorry.
But we need pre-processing
The
verification.
pre-processing.
Right.
Yeah, in
Is
the
what I'm-
previous.
Yeah.
And which part of the proof is non-uniform? It needs to be
No, I
non-uniform.
just meant that the description of the computation is not uniform. So F is given as circuits, not as a
Oh,
Turing
you're
machine.
given circuits.
Yeah.
Okay.
Yeah. The actual algorithms are uniform.
So as far as I recall, we don't know public encryption from SIS. So is this
We don't know what?
public encryption from SIS?
From SIS? That's a good question. Do we know public encryption from SIS?
I don't.
I don't know. Maybe not.
But I think that's a really interesting, assuming that's true, I think that's
I
really
see.
interesting as a...
True. I don't know how to think. Depends on the parameters, I guess. You can get trapdoor functions from SIS.
You can, okay, for your parameters, I think you can get trapdoor function.
It's whether you're in injective mode. In injective mode, you can do hardcore bit, but yeah, maybe we can take that offline. Yeah, but there are parameter regimes where we believe SIS is a weaker assumption algorithm. Any questions about that?
So your axis about your proof, sorry, I don't understand. So it says, which one doesn't use algebra? Your thing doesn't use algebra? I don't understand what...
X is a drawback, not...
It's a drawback.
Oh, sorry, yes. X is a drawback of the current work compared to prior works. So the drawback is that we don't get constant size proofs, whereas prior works get constant size proofs.
And the X is the weak.
Yeah, can you repeat
Semantics.
the answer about the p-poly? Why is that an X and not a
Yeah. Because
check
you need
line?
the pre-processing.
Oh, I see. In general, this is getting P is a harder problem than getting P/poly.
Well, it's not clear because P is smaller than P/poly.
Yeah, exactly.
True. Yeah. But then in general, if you can do P, there are standard mechanisms that give you P/poly, but not the other way around.
No, I think the point is it's because your P/poly, if you can do it for P too, but you will still need, because P in particular is P/poly, but you will still need a pre-processing.
True. Right. I
Others
see what you
don't
mean.
need it.
Right. Yeah. That's a good point. Yeah. Let's take some of these details off.
So if you can do for P, you can also do for P/poly on the pre-processing model?
Sorry. What's the question again?
If you can do P, then you can also do any P/poly circuit in the pre-processing.
More or less, yeah.
So pre-processing.
Yeah, exactly. Yeah.
And the proof is linear in the weakness.
The proof size is just depend on circuit depth. It doesn't depend on the length of the weak. There's no weakness.
The
This is
verification
P,
time is
not
linear
length of the
with the
inputs
weakness. There's no
and not the circuit. Yeah, this is P. Deterministic computation. Any more questions? Okay, good. So, right. So, in fact, in this work, we actually construct our results follows from the construction of a more general primitive, namely that of functional commitments. Okay? Let me say what functional commitments are. It's going to be slightly different from Pratyush's talk yesterday, but more or less the same. In functional commitment, you have a CRS again, and you want to commit to an input X. Okay? And when you want to open, you don't want to open just to X, but when the open algorithm gets as additional input a function F, and you want to open to f of X. And then the verifier, there's a verification algorithm that checks whether basically y equals to f of X. It checks the opening to see if y equals to f of X. As before, we're going to be interested in the setting of functional commitments for deterministic computation. So here F is again either a Turing machine or a circuit, mostly circuit actually. And similar to before, we want the commitment and the opening to be very small, sublinear in the length of X, and we want verification time to be fast. Okay? So for circuits, by fast verification is the same sense as before. Online verification is fast given a possibly slow pre-processing phase that depends on circuit F. The correctness requirement says that, well, if you commit to a sigma, you compute an opening for F correctly, then the verification algorithm should accept. And binding just says that given you cannot open a commitment to two different values. Okay, so this notion of binding is much weaker than the notion of function binding and extractability that Pritish talked about yesterday. In particular, there's no guarantee of any notion of consistency. Okay, so you could possibly, even if the verifier accepts, there's no guarantee that even exists an x that's consistent with f of x. It just says that you cannot open f to two different values. Okay. We can also define a notion of strong binding, which is the analog of strong unforgeabilities for signatures, which says that not only can you not open to a commitment to two different values, you cannot open, you cannot even provide two different openings to the same value. Okay? Yeah.
So what's the guarantee? There's no guarantee that has to do with
The only
x?
guarantee is that given any commitment, you can open to two different values.
But there's no connection to x? There's
There's
nothing
no connection
about
to
f? Nothing.
Yeah.
Okay, but this seems like harder to get than SNARGs, because if I have a SNARG, like this.
This is how they work. So we construct this object so we get a stronger
Okay,
result.
good. Okay, so this is stronger than SNARGs.
Yeah, this is stronger than
Okay,
SNARGs,
good.
yeah. In fact, this is exactly for deterministic computation, functional commitments for a class implies SNARGs for the same class. Okay. And here, so this is where for deterministic computation, the binding notion already gives you a notion of soundness. Okay. And the proof basically follows from the fact that, well, what is the SNARG given a functional commitment? The SNARG proof is going to be the opening pi. Okay. To verify, you just run the functional commitment scheme, which is deterministic, the commitment is deterministic, on the input, and then run the verification algorithm on the proof pi. Okay. And binding, correctness plus binding gives you soundness. So correctness will allow you to provide a proof to the, if it's a no instance, you can provide a proof, you can compute a proof to open to no, and binding says that you cannot, if you can provide a proof to both a yes and a no, then you break soundness. All right? Where the no you get from correctness, and then the yes you get from soundness. All right? And then they break binding. Okay.
Wait, sorry, why is the verifier doing the commit?
I'm sorry?
Why is the verification doing the commit, not?
Why is the verification doing the commit? Right. So here, you can do one of two things. You can either provide the commitment in the proof, which you don't need to do because the commitment is deterministic.
Oh,
so the verifier
okay,
can just compute
got it.
the commitment by itself.
I see.
So here, the verification algorithm for functional commitment is to take the input the commitment. So you have to, somebody has to provide the commitment.
But the commit will affect the running time of the verification.
You can either do pre-processing or the commitment takes linear time anyway.
Okay.
So your verification for SNARG will take linear time.
If you think of the functions f as circuits, but the verify is sublinear, or you think of them
I think of I think of f as a circuit. So a lot of pre-processing depends on the circuit f, and after you run in time independent of the circuit size.
And in that case, you also the SNARG you get is with pre-processing.
Right. Yeah. For circuits, it's inference inherent.
Yeah.
You can also additionally think about pre-processing dependent on x. Then you can also get verification time that's independent of the length of x. Okay. But mostly we think about pre-processing dependent on the circuit f. Any questions?
Hoeteck?
Yeah. Hi.
So I know in many other like SNARGs from the SNARG for deterministic computation, we get like throughout the same process we get also SNARG for RAM, where the verifier does not know x. Do you know if like in this way we could extend it to RAM or?
Good. So we don't know how to. RAM is closer to Turing machines. In fact, it's sort of a harder version of Turing machine, so we don't know how to do uniform computation. And here, if you are already given a hash of x, then you don't have to recompute the commitment to x.
So RAM SNARG implies you can use RAM SNARG to get this function commitment. That's kind of the point.
You can do that. Yeah. Any questions? We can take that offline. So that's basically the syntax for function commitments. So our main result is, so let me just say that strong binding for functional commitments gives you unambiguous proofs for SNARGs. So basically we construct functional commitments as strong binding, and that's where the unambiguity comes from. So our main result really is actually a new functional commitment scheme for circuits from the SIS assumption. The CRS is constant size, poly in the security parameter. Commitment has constant size. Again, constant is ignoring polynomial factors in the security parameter. The opening grows with the depth of the circuits, linear in the depth. The verification time, the online verification time after preprocessing is linear in the length of x. And this immediately gives you, via the generic transformation, the SNARG for circuits. So for the rest of this talk, I'm only going to talk about functional commitments. Right. Also, we get a transparent setup for the functional commitment, and we get strong binding. That gives us our transparent setup for the SNARG and unambiguous proofs for the SNARG. Right. So let me just say that the prior works for functional commitment for circuits, at least the one based on lattices, rely on non-standard lattice assumptions, and also in general have much worse parameters. They have additional factors that are pointing in the depth of the circuit. So compared to previous lattice-based functional commitments, the algebraic ones at least, this result is actually a very a substantial improvement over the state of the art. All right. So before I talk about the construction, let me quickly remind you what the SIS is.
We have them under LWE, right? So what do you mean?
We know how to do it from LWE. You're right. So here I'm really only talking about the direct algebraic constructions.
Okay.
Rather than the one that passes through SNARGs and.
I see. Got it.
Yeah, the comparison with LWE is sort of on the previous slide.
Got it.
Okay. Good. But our construction is closer to this kind of construction that's algebraic and direct. Right, so let me first do a quick recap of the SIS assumption. The SIS assumption just says that given a wide matrix A, it's hard to find a low norm non-zero vector such that A times Z equals to a 0 mod Q. Right, so assuming here are a couple of distributions, assuming the standard SIS assumption where A has a uniform distribution, here are a bunch of distributions for matrices for which they are SIS hard. But SIS hard, I mean, it's hard to find a vector Z such that blah times Z equals to 0 mod Q. Right? For instance, the following distribution is SIS hard. So if you have two copies of A, it's going to be hard to find a non-zero vector such that this times Z equals to 0 mod Q. Just because, you either break the top copy or you break the second copy of SIS. Okay? In fact, the following distribution is so SIS hard. If you put any arbitrary matrix here, it's still going to be a SIS hard. Roughly speaking, either you break SIS on the top column, or the top column are equal on both, then you break SIS on the second column. Right? The top column is non-zero, then you break SIS with respect to the first A. If the top part of the vector is 0, then you break SIS on the second A.
Sorry, I missed it. What do you mean SIS hard?
Good. SIS hard I just mean for this matrix, where A is chosen from the uniform distribution, it's hard to find a non-zero vector Z such that this matrix times Z equals to 0 mod Q.
Sorry, 0, 1. Sorry, low norm Z?
Low norm Z, yeah.
Okay.
Yeah. So this is a SIS hard distribution for any A that's uniformly random, and essentially any random matrix.
So basically you're saying for random A, it's SIS hard, but also there's other distributions that are not random.
That follows from...
For those, it's also SIS hard.
Right, that follows from SIS for the uniform distribution, yes.
Are the two A's there denoting two independent samples or copying one sample?
The A's?
Yeah.
It can be the same A.
Same A, but okay. So
that's the concatenation of two hash functions.
But so you mean here like sample once and plug it in?
Yeah. It's the same A. Any question? Okay. So the following distribution is also SIS hard, so you can repeat. And then there's the more interesting ones. For instance, if you take a uniformly random 0-1 matrix, that's also SIS hard. Right? That sort of follows from the work by Dan and his former students on. They sort of prove this in the context of LWE. And the proof basically is fairly straightforward. So if your U times Z equals to 0, then A times Z equals to 0. Okay. Also, if you take a uniformly random matrix A and multiply it by uniformly random 0-1 matrix, that's also going to be a SIS hard distribution, even if you know A and U. Right? And here, basically, you are either going to break SIS for U or you're going to break SIS for A.
Wait, sorry, is U 01? Oh,
U is 01, yeah. More or less 01. It's really the bit decomposition of a uniformly random matrix mod Q. So if Q is a power of 2, it's 01, otherwise it's slightly off, but that's sort of fine. Okay. This distribution is also SIS hard. And moreover, the following distribution is also SIS hard. If you pick two uniformly random matrices A1 and A2, pick two uniformly random matrices U1 and U2, and then consider all four possible products and arrange them in a row. Okay, if you concatenate everything together, this is also a SIS hard distribution. All right. This basically follows from the fact that you can decompose it into the product of two matrices like that, and then sort of apply the previous result. Okay? And we crucially use the fact that this thing is low norm. Right? This is sort of this again, implicit in the BRMR argument in the LWE context, and it's sort of in some sense, some notion, the lattice analog of the Naorango argument. All right. So these are the kind of distributions that we'll be seeing in our construction later. All right, let me first start with a warm-up by describing a weaker result for functional commitments for circuits. This is a result that, this is a construction from my earlier work with David, and with some improvements from my paper at Crypto. All right. So we're going to construct functional commitments for circuits from a variant of SIS. This is going to be a non-standard variant of SIS, and then later on we're going to improve this construction to achieve security under standard SIS. And it's going to also achieve very bad parameters. The CRS here, okay, the constant here not only hides polynomial security parameter, but also hides polynomial depth of the circuits. Okay, so this is quite a bit worse than the previous construction, but never mind that. The CRS is pretty large. It's going to be quadratic in the length of the input x. The commitment size is poly depth of the circuits, and the opening is also poly depth of the circuits. Moreover, verification is slow. I don't know how to do fast verification even given preprocessing. Okay. So we'll see this construction, and I will have to solve all of these problems to get to our main result.
Wait, what do you mean by slow? Like doing the computation?
Yeah. But for commitments, it's not the same as for SNARG. That's a trivial construction. For commitment, that's not true. Because you don't get x in particular. Questions? Good. Yeah. So verification basically, even after preprocessing, you have to recompute. So here's the construction. Good. Here's the warm-up construction. So the CRS is going to contain a essentially LWE matrix, rather a SIS matrix B. That's wide of dimension n by q. N by m. Okay. Think of m as like n log q. And then there are a bunch of matrices W1 up to WL. That's wide, same dimensions as B, uniformly random. And a bunch of square 0, 1 matrices, BIs. So the CRS so far has size L, is going to become bigger later. All right. The commitment to X, think of X as a bit string of length L, is going to be essentially the lattice analog of the Pedersen commitment. It's going to be sum of Xj, Wj. Now, the idea for this construction is that, roughly speaking, we want to be able to take the commitment and expand it using a matrix VI into the CRs into a GSW encryption of Xi under the matrix B. Okay. So basically, you can think of C as a compressed version of a GSW encryption of X1, X2 up to XL. Why is this useful? Suppose you can expand C into a GSW encryption of Xi's, then you can do homomorphic computation on this GSW ciphertext to obtain some evoked ciphertext C sub f, which corresponds to an encryption of f of x. Okay. Moreover, this homomorphic evaluation has a property that if you know the randomness for the original GSW ciphertext, you can derive the randomness for the evoked ciphertext. This was shown in the work of Daniel and Sergey and Vino in the context of homomorphic signatures or homomorphic commitments.
Why is it the case that C times VI is equal to this?
This is what we want.
So
suppose you can get this.
Okay, so the WJs and the VIs are not just random. You're going to choose them in a way that.
Good. So far they are random. I'm going to put more stuff to enable me to do this.
Got it. Okay.
So far they're random.
Okay, good.
Yeah. So right. So this is what I want to be able to do. I haven't told you how to do it yet. Suppose you can do this.
Okay.
Then with homomorphic evaluation, you can compute an encryption of f of x. And then your opening will just be the randomness for the encryption of f of x. And the verifier just re-encrypts the randomness to see whether it gets to the ciphertext C sub f, which you can compute from C times B sub I. So the reason verification is slow is that you need to perform homomorphic evaluation, which I don't know how to decouple into an offline phase and an online phase. Any questions about the high-level strategy?
So how many, in this version, how many evaluations do we need? As large as the circuit for S?
Yeah. Basically the circuit size. Yeah.
Okay. So
the running time is circuit size times polynomial in the security parameter. Times polynomial circuit depth.
This is the prover does that.
This is the verifier does that.
The verifier does that?
Yeah.
So you haven't saved anything?
Yeah, the verifier, you haven't saved anything, yes. For functional commitments, even if the verification is slow, it's still a non-trivial construction. For SNARGs, the verifier can just redo the computation by itself. In functional commitments, the verifier doesn't know X, so it cannot just redo the computation by itself. So we're not saving on computation. We'll have to solve this problem later.
You need Z to be no norm in that case?
Yeah, Z, we will need Z to be low norm. Yeah, I'll say that in a second.
So you have some kind of set of function that you can support?
Yeah. I need to explain to you how you compute a Z sub I that corresponds to GSW randomness for the ciphertext C times V sub I. I haven't explained how to do this yet.
Because, so again, C times VI is public, right? So this all...
C times VI is public.
Okay.
Yeah, C is part of the commitment, so you see it. VIs are from the CRS. Right? So you really have this small commitment that has size independent of L, which can expand into LGSW ciphertext. So this is the compressed GSW. Roughly speaking. Or rather, maybe it should be called compressed GVW, but we'll call it compressed GSW. Any questions? Okay. And now the algebra comes in. Okay, good. So what does it mean to be a GSW encryption of X? This is actually a GSW commitment, but let's ignore that distinction for now. That means that Zi, the random, should satisfy the following equation. So C times Vi, so the following dimension, is equal to B times Zi plus Xig. Okay, this is the equation that we need from what it means to be a GSW encryption of Xi. Okay, and Zi needs to be low norm. All right, this is what the prover needs to be able to compute to provide the opening. So it needs to, given the CRS, which needs to contain some additional helper terms, together with X, it needs to compute, be able to compute Zi that satisfy the following equation. Now, so what additional helper information do we need to provide in the CRS? This is where the quadratic draw comes in.
This GSW encryption is being an encryption under SIS.
This is a...
the SIS version.
This SIS version is actually a commitment, yeah.
Okay.
So in particular, there is no decryption key for B.
Exactly.
Yeah. Good point. Yeah. But right. Yeah. I'm just going to say GSW encryption so that it's more familiar for people who. But it's actually just a commitment scheme. Yeah. Okay. Good. So how do we get something like this? Now, first, let's try to expand C times Vi. Okay. C, remember, is sum of Xj, Wj. So you multiply C by Vi, you get terms that depend on that depend on I, that looks a bit like this, which can split into two parts. The Xig part that matches this, and then there's a Wivi part that comes up here. This cancels out this term over here. All right. And then you get a bunch of cross terms that comes from the interaction from I not equals to J. All right. Now we want this equation to match this equation. So this cross term plus this term over here is going to be B times Zi. So you should be, so Zi needs to be essentially the pre-image of this term under B. Low norm pre-images of these terms under B. Okay? So to be able to compute this term, I'm basically going to compute Zi as follows. I'm basically going to sum it as low norm pre-images of each of the terms in the sum. And then to get these terms, I'm going to put them in the CRS. Okay. So the CRS is going to have size roughly quadratic in L. It's essentially going to allow me to compute all of this, contain the pre-images of the cross terms, and contain pre-images of the diagonal terms minus G. Okay. Any questions? And then when you multiply by Xi, you get exactly, when you multiply back by B, you get exactly this equation over here. So it's basically B inverse of each of these terms. Right? And we're assuming the x's are 0, 1, so when you multiply by 0, 1 values, you don't blow up the norm either. Okay? So the CRS contains low norm pre-images of all of this term. That's where the L squared comes from. And this is going to be a structured CRS. Okay, questions so far? All right, so binding essentially will follow from the fact that you just have to trust me, that B is a hard cis instance. It's going to be hard to solve cis with respect to B, even given the terms in CRS. But since the terms in the CRS contains pre-images under B, this is not the standard cis assumption.
So why is Zi not low norm?
Why is the Zi low norm? Yeah. Good, because it's going to be a low norm linear combination, because the x's are low norm, of these terms, and these terms are in the CRS, and these terms are going to be low norm. So the B inverse will be a low norm Gaussian pre-image of this terms under B. The Gaussian is also not that important. We're going to be getting rid of all of these cross terms so that we get a uniform CRS. Okay. Any questions? Okay. All right. Good. So, right. So our goal. This sort of gives the basic construction. Our goal, remember, is to get to the SIS assumption. All right. And towards this goal, the main idea is to come up with a relaxation of this equation, which corresponds to
the previous. Sorry, go to the previous slide. You can prove that this construction is cis hard, right?
You can prove that this construction, good. You can prove that the construction binding, assuming that B is cis hard, given the terms in the CRS.
You need to assume that.
Yes, yes.
Oh, okay, so
and
that's
the
not
assumption.
standard.
That's not standard cis.
Oh, okay. Right. Because you have like this trapdoor or whatever.
Right, yeah, exactly.
Okay, so now you're gonna.
But the assumption has nothing to do with circuits and there's nothing to do with.
Okay, but now you're gonna try to get to just do it under standard cis.
Right.
Okay.
The goal is to get to standard cis.
Good.
And towards this goal, we're going to relax the invariant that we have, namely that we can expand C into a GFW encryption of XI. Okay, we're going to relax this. And the relaxation is inspired by the recent stock paper of Damiano, Giulio, and Lance. Good. The relaxation in particular will allow us to get rid of these cross terms. And this essentially is what's going to give us binding from the standard cis assumption. However, so it buys you something, but it loses two things. First, C times BI is no longer going to be a GFW encryption of XI. So you can no longer perform homomorphic computation of C times BI. But it's still going to be able to support some limited notion of homomorphism, and we're going to try to leverage that to be our scheme. Okay. Another drawback is that the opening ZIs now are no longer going to be constant size. It's going to be quadratic in the size of the inputs. Okay. And we'll have to find a way to make this thing smaller also. All right. So in the rest of this talk, I'm going to explain what the relaxation is and how you prove security from the standard cis assumption. And then I'm going to show how to get the homomorphism from this relaxed equation, which I haven't said what it is yet. And finally, I'm going to explain how to compress the size of the openings. And these three components are going to be somewhat orthogonal. So if you miss any of them, you can still catch up on the other ones. Okay? Any questions for the high-level approach so far? Okay, good. So we're going to start with one, and that's why we have to do a lot of algebra, because we have to figure out what the relaxation of this thing is, which is inherently an algebraic relation. All right, so we want to relax this equation. The first thing we do, we're going to move the xig from the left-hand side to the right-hand side, from the right-hand side to the left-hand side. Then we're going to take the left-hand side and split it into the top part and the bottom part. Okay? So the left-hand side is now going to look like this. It's going to be twice as tall as the previous thing. All right. B is also, just to be consistent here, B is also going to grow twice as tall so that it can match this thing on the left-hand side. Okay. And B is going to become a lot wider by a factor of L squared. Okay. And that's why the height of Z is going to grow by a factor of L squared. That's why your opening is long. Okay. So what does B look like? All right. Now B is going to look like the terms that we were putting into the CRS. Right? Except we look at what they are pre-images of, which are terms of the form Wi Vj minus delta ijg. So delta ij is 1 if I equals to j and 0 if I not equals to j. Right? We're going to take those terms and do the same thing. We're going to split them up, top and bottom. Right? So we're going to stack the terms this way and stack them horizontally. Okay, this is our new B. So B, our new B is now a structured matrix. It's going to be fully determined by the Wi and Vj matrices. Any questions? And that's our new equation. So this is what our new equation looks like. Okay. This thing is split top and bottom, and then we stack off the essentially all of the cross terms horizontally. All right. Any questions? Okay. Let me first say correctness holds. Basically, for the same reason as before, you can split this sum into the terms that depend on I and the terms that don't depend on I. Okay? And then all of these blocks here appear as columns over here. So the linear combination of the xi and xj will go into the opening zi. Right, so correctness follows essentially from before, So your Zi nows were, unlike before, which contains terms that depend on terms of the CRS, your Zi now are essentially, it's going to be a 0-1 matrix where every entry is something like 0 or xi or xj. Good. Binding. Good. So I'm going to claim that under the SIS assumption, B top, which is the top n rows of B, is going to be a SIS hard distribution. All right. That basically follows from the BLMR proof, since this is just a product of a pairwise product of a uniformly random matrix with a low norm matrix. Okay. So B top is going to be a hard SIS instance, and basically this will give us binding. All right. Because basically whenever you have the same commitment, you're going to, the left-hand side is going to be the same, and since it's a SIS hard instance, it means that the two openings are going to be the same, and if the two openings are going to be the same, they're going to multiply the same thing over here, so you're going to get the same value over here. Okay. So this basically, the fact that B top is SIS hard will give you both binding and strong binding. Because strong binding against, you find two different things that open to the same thing over here, then you immediately break SIS. All right? So that's the whole construction. So it's a new commitment from SIS, which has a very different verification equation from the usual SIS-based commitments like the I-type-based I-type-based commitment or the new tree-based variants of the I-type commitment. Questions? All right, so that takes care of our basic construction. Now we have to worry about homomorphic multiplication. All right. So previously, because these things are stacked together, you can do your standard GSW homomorphic multiplication. Now they are stacked on top of each other, it becomes a little bit harder. Okay? In particular, what does homomorphic multiplication mean? Suppose you want to multiply x1 by x2. So you're given openings to x1 that satisfy this equation, opening to x2 that satisfy this equation, and you want to derive an equation of this form, all right? Where you have C times some D that depends on 1 and 2, so depends on matrices and CRS, with x1, x2, g at the bottom. Okay, this is what you want to get. All right. So how do we do this? So we're going to try to mimic usual GSW homomorphic multiplication. Okay. So we're going to try to get the x1, x2, g over here by multiplying this equation on both sides by x1. Okay. Then you get this term over here. You want to get rid of it by you want to get rid of this equation here by multiplying this one by, I think there's a typo somewhere. Wait, this should be an x1. x1, right? Yeah, that's x1. So then you multiply both sides by, I'm so sorry, this should also be an x1.
Yeah.
No, wait. Either that or, yeah, this should both be an x1.
Yeah, everything is x1.
But this two anyway should match up. They should both be x1. Okay? So then now you want to cancel these two terms out, except this thing at the bottom and this thing at the top. Okay? So what you do is first, let's think of B as having two parts, B top and B bottom. So far I haven't done anything. And then I'm going to pad the matrices so that this term and this term appear at the same place. Right? So I want, right, so I'm going to pad this one by zeros at the bottom, and then the other one I'm going to pad zeros on top. Okay? Now, this cross term is going to appear in the middle, there's another typo here, that, so that they match up. All right. Then now you can add the two things here, and that gives you your new equation. So your left-hand side grows. There are extra zeros in the middle that comes from the cross terms. These extra zeros don't appear in GSW or BGG+. And this matrix B also grows. Okay? And that's sort of okay. Let me just first say a few other things. It's not always okay, but it's okay for degree 2 for now. All right. The next thing we want to do is actually we want to be able to rewrite the top part as something that depends on C and something that depends on B. This is useful for fast verification and to handle general degree 2 polynomials. Because this gives you linear homomorphism, then you can add many degree 2 monomials together. All right, how do you do this? Oh no, sorry. Oops. Oops. Pięci. How should I do this? I think the cursor is on this thing. Ah, okay, thanks. It's good. Oh, sorry, thank you. So I had to borrow a laptop. Don't ask. Good, right, so I want to be able to rewrite this expression in terms of something that depends on C multiplied by something that depends on B. Okay? I'm going to do this using a technique from my recent Eurocrypt paper. Right? The first thing I'm going to do is going to move this bracket into the inside. Right? Which you can do. You can move the bracket on the inside and still everything is going to be small. Because whether you do G inverse of C times B2 or G inverse of C times B2, this is still going to be small because B2 is small. All right? And now you have product of 4 different things. Right? You can then use magic the tensor products and vectorization and basically switch the order of these 2 terms. Okay? And once you switch the order of these 2 terms, then you get something depending on C multiplied by something depending on B. Right? It's just basically the point here is that these are all, degree linear function in C and V, so you can sort of switch the order of the linear function. All right? And then this is going to be our new C and this is our new V. All right? And the nice thing now is that you get fast verification for degree 2 polynomials, since you can basically get, this corresponds to every monomial in a degree 2 polynomial, and you can add across different monomials. Right? That gives you general degree 2 polynomials. So that's good. Except the problem with this construction is that for depth D circuits, it incurs a 2 to a D blow up. Basically, for degree D computation, the dimensions grow with D. And a depth D circuits can compute computation of degree 2 to the D. All right? So to solve this problem, we're going to take a combinatorial approach. So if you don't have the algebra so far, now we're going to go back to doing something combinatorial, which is we're going to take a different approach to try to get to functional complement for circuits. And this is a notion of a chainable functional complements. It's related to RAM SNARGs, but not quite. Okay? So a chainable functional complement is like a functional complement scheme, except verification changes, the verification algorithm behaves a bit differently. Okay? Instead of getting the output Y, it gets a complement sigma prime. And instead of trying to check whether Y is equal to f of x, it's trying to check if sigma prime is a commitment to f of x. Okay? So it takes as input 2 commitments and want to check if they correspond to commitments to consistent computation in some sense. Right? So correctness says that if sigma prime is indeed a commitment to f of x, the whole thing accepts. And binding just says that you cannot open a commitment sigma to 2 different commitments, sigma 0, sigma prime 0 and sigma prime 1. So there's no guarantee of consistency as before.
Right. But it's like uniqueness. You get kind of this unique. Okay.
Okay. So now, if you have a chainable functional complement for degree 2 polynomials, you get a functional complement for circuits. Okay. Where there's a blow up in the that's linear in the depth of the circuit. This is one of those statements that once you see it, you can sort of see what the proof is. And basically the construct is as follows. You have a chainable functional complement for degree 2 computation, and you want to get a functional complement for circuits. What do? Suppose you have a circuit of depth D. Think of it as a layered circuit. Okay? You're going to commit to, in the opening phase, you're going to provide commitments to every layer, the wires in every layer of the circuit. Okay, so the first layer is sigma 1, the second layer is sigma 2, up to sigma, the depth of the circuit. And then you're going to provide the chainable degree 2 openings to prove that every pair of consecutive layers are consistent. So every layer is going to be degree 2 computation, so you can you'll be able to provide the degree 2 openings.
But what is the value you're committing to?
What's the value that you're committing? You're committing to x. You're committing to x.
To the original x? You're not
sorry. The new commitment is the same as the original commitment. So you just commit to the original x. The opening is going to commit to it's going to contain commitment to the intermediate wire values. So you can only do this during the open phase because when you are committing, you don't even know what the circuit is going to be. So it's sort of the natural construction. During the opening, you commit to the layers, the wire values for every layer of the circuit, and then you prove consistency for every layer.
But the verification is all parallel, right?
Parallel.
I mean parallel in the sense that I don't. Sorry.
It's not interactive, right?
No, I mean the verify doesn't have to go in this order, right? Like it just verifies each.
Yeah. The verifier just sees the commitment to consecutive layers. It doesn't really need to know what's happening within the layer. Yeah. Okay. So the commitments are small. You really should think of the function as having long inputs and long outputs. Right? And the commitments are independent of the input length and the output length. Right, so this strategy was already implemented in the work of Carla Raffles and her student, and variants of this idea is also implicit in CJJ. Any questions? Yeah.
What's the sigma prime in this reduction?
Oh, what's the sigma prime? Good. So the sigma prime is the input to the verification algorithm. It's supposed to correspond to the commitment to the f of x. So the verification algorithm gets two commitments. One is a commitment to the input, and one is a commitment to the output. It's supposed to check whether these two commitments are consistent. That's the syntax. So when you are running the verification for the new functional commitment scheme, we'll run the verification algorithm for the chainable functional commitment on each pair of consecutive commitments, with sigma and sigma 1, then with sigma 1 and sigma 2, with sigma 2 and sigma 3, and so on and so forth. And it accepts all of them accepts.
Can you go back one moment to the definition of chainable? So which one was the chainable? Oh, you had something before this. It doesn't matter.
So the intuition, roughly speaking, is that the chainable functional commitment says that the second layer must be the correct commit. The first commitment must be the correct commitment to the values of the first layer, and then inductively it says that the next sigma 2 must be the correct commitment to the values in the second layer, and so on and so forth, and then that guarantees that your final output is correct.
The size of the commitment does not increase during this chain?
Yes, the size of the commitment in the end is going to be the size of the original commitment. The size of the opening is going to be basically that times the size of previous commitments plus that times the size of previous opening.
So in your previous construction, only the opening blow up to 0, not the commitment size?
Correct. Correct. The commitment size is always sum of XIWI. So this solves the 2 to the d. Any questions? So now it remains to construct a chainable functional commitment for degree 2 computation. Okay? And this we essentially get for free from our construction in the following sense. Good. Again, our goal is to, given a function f, which we think of having long outputs, so LB outputs, that is corresponds to function f1, f2 up to fl, each of which has a 1-bit output, each of which is a degree 2 computation. And our goal is to open to a commitment to fi. What's the commitment to fi? Is sum of fi x times wi. And this is the value that you want to open to. Okay. Now recall that we can open to a fi x. Okay. This just basically follows from the correctness of our basic functional computation scheme for degree 2 computation. And we sort of want the thing at the bottom to be this expression over here. So that is a commitment to f of x. So what do? You multiply both sides by g inverse of wi, and then you sum. That's it. Okay? That's the construction. So you basically get, because of the structure of our verification algorithm and the fact that commitment is essentially linear, we get the chainability property for free. Questions? Okay, so that concludes the second part of the construction, which is how to handle homomorphism when you don't have full-fledged GSW homomorphic computation. Right.
Where's the place we use that use degree 2 in this group?
What's the fact that we use the degree 2?
Yeah.
We use the degree 2. We use the degree 2 here in the sense that you can decompose the circuit into D layers.
I'm not talking about this. I'm talking about the next place.
And then here we use the degree 2 functional commitment for degree 2 polynomials to get to this initial equation, to be able to open to fix times g at the bottom.
If it's not degree 2, you cannot have this.
This is a degree 2 computation, so we can handle this using this
multiplication. I see. Okay.
And degree 2 is good enough because you can just split things up into degree 2. You can also handle degree 3, but there's no point doing degree. You do degree 2 as a sequence. You do degree 3 as a sequence of 2 degree 2. More or less. Not quite, but. Good. Yeah. So this concludes the second part. And the third part is how do we compress the size of the openings? Okay. Right now they're size L squared and we want it to be constant size. And to do this, we basically do a Merkle-style recursion. And the same thing was done in the Game Euroquick paper and also the earlier stock paper of Damiano and friends. All right. The base case is going to be 2m squared. Why 2m squared will be clear in the next slide. And the base case you can just instantiate from the scheme with long openings. Right? The openings is L squared, but L is now fixed. It's a fixed quantity that on M, which only depends on the security parameter. The recursive case goes from L over 2 to L. All right, how does the recursive commitment work? It's really a Merkle-style commitment. So suppose you have a vector of length L. You divide it into 2 parts, x0 and x1, each of which have length L over 2. Okay. Then you individually, using the recursive step, you individually commit to each of x0 and x1, which gives you 2 matrices of dimension n by m. Okay. You concatenate the 2 matrices together and take the bit decomposition of this matrix as a vector. So it's going to be 2nm log q, which is essentially 2m squared. So when you do a decomposition, you get a vector of m squared. And then you just commit to this vector. And that's where the base case of 2m squared comes from. Okay. And that's it. You commit, do decomposition, and commit. All right, so this is a tree-based construction. And the nice thing is that, I'm not going to talk about it, but basically, if you unpack everything, this Merkle-style construction also respects the linear property of the verification equation. Okay. One thing that happens, however, is that the dimension is going to blow up logarithmically in the length of L. So you're going to have to do a bit of padding, similar to the way we did the padding for degree 2 computation. So that's the entire construction. So to conclude, we presented new SNARGs for P/poly from the SIS assumption. The open questions are, extend these results to get to P for uniform computation, and to improve the proof size from linear in depth to constant size. Okay. So there's some sense that this you can potentially do from SIS. There's some sense that this you cannot hope to do from SIS, that you need to do LWE. Okay, that's a conjecture.
Wait. Oh, I see. You're saying that you conjecture that you can't shrink the proof size by relying on NSYS.
The circuit depth dependency, we don't expect people to do it without LWE. Right? But the uniform version potentially can be from SIS, which will be like a non-interactive version of GKR.
Yeah, exactly.
From SIS, but no LWE.
Yeah,
that seems entirely plausible.
Yeah.
Right. So let me just say a series of recent related works. So today I talked about how to do compressed GIW. You can also do compressed BGG plus ciphertext. Which roughly, you can take this BGG plus ciphertext, you can compress it into something that's constant size and expand it back to a BGG plus ciphertext using similar techniques. And this idea turns out to be very powerful. And it's already found applications to blah, 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 blah. Okay. Right, the conic function evaluation, which hopefully you will hear about. A beautiful paper, I hope you'll hear about it in the third workshop. Succinct randomized encodings, which you heard about in the previous workshop, Julio gave a talk. New distributed broadcasts, which David talked about in the previous workshop. And almost optimal ABE schemes, which David sort of talked about in the previous workshop. The KP part, not the CP part. Right, so I think there's still a lot more exciting things to be done in lattice-based crypto. Thank you.
I actually have a question. So I'm thinking about your construction from a high level, which to me, it really reminds me of GKR in the following sense. You tell the prover, compute the damping, the entire circuit. Computer and then it's a reduction kind of from layer to layer. That's basically what you're doing, but you're doing it all in parallel using kind of crypto as opposed to, So you're basically committing to each layer, and then you want to go from layer to layer. Now, so far, no circuits that can do Turing machine. You didn't use any non-uniformity. In GKR, going from layer to layer was done using some check. You're doing it using the SIS, using lattices. why is so for that part is where the pre-processing is inherent. Yeah?
Right. So there are
Why
few
can't you
things.
do
First of
the
all, in
following
GKR, you don't commit to every layer.
Well, you kind of do when you
can do it.
When you convert it into like an argument, then succinct, then basically that's what you
That's
do.
what happens.
But forget about it. Yeah, think of it like the idea is you take a layer, you kind of, in GKR you can do committing to everything altogether, but it doesn't matter. You kind of reduce it. What you're saying is you're saying, look, I have a big circuit. I'm going to reduce it to just looking at one layer of the circuit. Right. That basic idea. Now, the question is, how do you do this? So you do it under SIS, which is fabulous. Why is the non-uniformity so important there? Because you can.
Good. What is non-uniformity? First of all, good. So certainly we need to enable pre-processing. So the pre-processing certainly uses an algebraic structure to be able to, so that you can do this thing in 2 parts, right? One thing that SUMCheck allows you to do is to really reduce the computation to something that's logarithmic in the domain size, which is the number of wires of each layer, which is something that we don't do here.
Okay, so you're saying basically what you're saying, when you talk about lattice-based cryptography in this setting, you will need to do kind of matrix per kind of width in some sense, like per layer.
And then we are able to, using homomorphic property, compress all of these computations into a pre-processing phase, but we're not able to, suppose this computation has more structure, like in a uniform setting, we don't know how to compress the computation so it's fast. We can only compress the size. Even when it's structured, we don't know how to leverage the structure of this intermediate thing to speed up the computation.
Yeah, I see. I think.
So sort of, if you think about this, roughly speaking, this V sub F matrix for F that's the degree 2 computation is sort of where this degree 2 preprocessing happens. And even if this F is very structured, which is sort of has a small description in a uniform sense, I don't know how to compute V sub F very quickly. I will still unwind the entire computation and compute the whole V sub F. So there's some sense that for structured computation, V sub F should have a faster computation algorithm to compute V sub F. But that's something that we don't know how to do yet. And that's something that we don't need to do either if we're in the circuit set. So we are cheating a little bit. So there's a very big gap between, in the sense, P/poly and P.